We have 6 wonderful talks for you guys today. These are tight 5-minute talks that are meant to give you a taste of a project. There's just so much going on, and one of the points of CalBEM is to circulate ideas, to make people feel like they have an idea of what's going on in the community, like what's everyone working on, what's the cutting edge right now. The only way to really feel like that is to hear from everyone. So we have this series of flash talks. I'd like to welcome Ben Lalor to the stage for his first talk, and on deck is Rongxin Yin.
All right, hello everybody. My name is Ben Lalor, for those of you who don't know me. I have a background in building energy models for code compliance in California, and I currently support some of the publicly available code compliance software tools, such as the Virtual Compliance Assistant and Zebiak. So as many of you guys know, every code cycle, the standards evolve, and there's a huge amount of effort that goes into determining what those changes should be. And we hold workshops, we gather stakeholder feedback, and we debate proposals, all in an effort to really understand what's really happening in the market. And once the standards are adopted, the work doesn't stop there. We have training materials, technical resources, and software tools that all need to react under tight timelines to support those new changes. And one of the challenges in all the decision-making that goes into those things, in both developing the standards and the resources and tools that support them, are that many of those decisions are based on subject matter expert opinions or perspectives, stakeholder feedback, and fragmented data from different sources. And all of those do hold value, but they can also be biased or only represent a small slice of the market or a certain perspective. So what I believe is missing is an objective statewide data set that can tell us how buildings are demonstrating compliance in practice. A data set that can help us answer questions like which building types are using which compliance methods and in which climate zones. So that's what we set out to build. We're trying to build a data set that can help us understand how buildings are being modeled in California, so we can start making decisions based on objective facts. And the need for better data has been recognized for a long time. Just last year here in Sacramento at the National Energy Codes Conference, that message was stated very directly. Commissioner Andrew McAllister emphasized the need for, quote, building data-rich analytical tools to support code changes, policy decisions, and program implementation. So here's a high-level view of that data set. Currently, today, it represents over 268,000 unique compliance forms across 179,000 unique projects. The data comes from multiple compliance tools, represents both prescriptive and performance compliance pathways, covers the 2019 and 2022 code cycles, and represents non-residential, high-rise, and low-rise multifamily. So when we started digging into the data and doing some data analysis, we ran into some surprising truths that I can share with you today. One of those surprising truths came to us when we used the data to help inform a Cal MTA study on efficient rooftop units. I think I saw Garth in here somewhere, but he was a program implementer there. And they came to us trying to explore some electrification policies, and they were trying to understand what type of HVAC systems people are installing on their rooftops, specifically what percentage of those rooftop units were heat pumps. And the assumption was that we were going to find a relatively low market share in the 2019 code cycle, but moving into the 2022 code cycle, we expected we would see acceleration of that market share with the adoption of those single zone system type requirements that specify heat pumps in most cases. But what we found was that in the 2019 code cycle, the majority of systems were heat pumps, and that was continuing to accelerate into the 2022 code cycle. You can see the blue line represents prescriptive products, and the orange line represents performance projects and their market share of electric HVAC systems. We used the data to answer another age-old question, prescriptive versus performance. And the assumption was that the performance path would dominate, but that's not what we found. When we looked at the data, we saw that the majority of projects are actually using the prescriptive method to demonstrate compliance. You can see here, Envelope is the largest adopter of the performance method at 54%, and Mechanical is only using it 23% of the time. We also use the data to look at the average delta between compliance credits and penalties across the compliance categories. A lot of us were surprised to see how much savings is being had in fans and PV and battery. And so we're working with CEC and CASE teams to help understand where buildings are being built beyond the baseline building specifications so we can potentially increase the stringency in those categories. And finally, I just wanted to say that this has been a really long time coming. I'd like to thank Jill Marver of PG&E for her vision in helping make this work possible. And we've built a really strong foundation here. And so the next steps for us are continuing to gain value from the data set. And so if any of you guys are working on a research project, a policy, a program, and you think you would benefit from real-world compliance data, please reach out to me, and I would love to see how we can help support your work.
I would also like to thank Jill Marver just for being so awesome, generally. Up next is Rongxin Yin, and on deck is Greg Collins.
All right, good afternoon, everyone. I'm Rongxin Yin with Berkeley Lab. Well, this is my topic, which is CO2 heat pump. And the unique of this heat pump, it can produce heating, cooling, and domestic hot water simultaneously from one single power source, which is electricity. And the other feature of this unit, which is like, it has advanced energy balance control and defrost design. So as we know, traditional heat pumps, they may have some defrost issue with that impact on the efficiency, but this one, no defrost operations during the extremely cold conditions, even though. And let me point out here, this is the heat pump unit, and that's shipped to our first lab for the laboratory testing. And this unit, which is 20 tons unit, and which is about like 1/3 or half size of the 10 tons, existing air-cooled chiller and natural gas boiler. And it has three, it has like separate 6 pipes, 2 for each loop, heating and cooling and domestic hot water. So which is very easy for plug and play to our existing hydronic systems. So as I just pointed out, and for this demonstration of the CO2 heat pump at the first lab, and it's just the unique feature with the plug and play. We swap out the existing air-cooled chiller and natural gas boiler and keep using the existing hydronic systems to provide the cold water, hot water, as well as domestic hot water to this test bed. And just like it, as I just mentioned, simultaneous heating cooling, as well as hot water at the same time. And it's just a matter of how the building needs that load requirement. I just give you a few shout out about our test bed. And basically in our first lab, we set up a test bed to represent the typical commercial office buildings. And it has some operation mode. So basically during the spring season, we have the heating load in the perimeter zones, and we still have the cooling load in the core zones. That we have the simultaneous cooling and heating need. All right, regarding the performance of this CO2 heat pump, well, since over the 12 weeks testing period, we, this heat pump reached to low range of the target performance target. And for the cooling only mode, the test COP of the heat pump is ranked from 2 to 4 of the cooling only mode, and 1.8 to 8 to 2.3 for the heating mode, and for domestic hot water, it's about 2 to 3, 2 to 4 of the COP. Surprising, I need to point out the unique feature, which is high COP of the simultaneous mode. So it's like it's similar as like a heat recovery chiller, but way different. So besides the the performance of the heating and cooling and the mass power mode, and this heat pump is also kind of like it has very it has like capable of demand flexibilities in terms of either doing load shed or load shifting by manage the temperature set point of the heat pump. And I need to point out, as just mentioned, if you have very well balanced heating and cooling load operation in these buildings, you can have up to 4 to 6.5 of COP, which is very high, which means, but it also provides another opportunities like how I can enable the heat pump running at a simultaneous load, balanced operation conditions. So if you can integrate some storage to balance out heating and cooling in a simultaneous mode, you can have very high COP of this CO2 heat pump. All right, that concludes my today's talk. Thanks.
Thank you so much, Rongxin. All right, up next is Greg Collins, and following that is Michael Sawford.
All right, it's my 10th CalBEM. Pretty proud to be able to say that. It's pretty cool to attend that first one and see the progression over the years. Also really, thankful to be invited to come back and give another power talk. The topic shifted a little bit, kind of zoomed out one level from what was in the program, although I am providing an update on that project. I wanted to share 3 others that have been that are still relevant to CalBEM and some of my power talks of years past. So the first one, 3 years ago, actually, I had a power talk that was on BEM Toolbox. So it's a web platform that my company developed to provide free energy modeling tools for automation and reporting. And everything here is kind of under the theme. Something we've been working hard at doing is modernizing reporting and reporting tools for BEM. So that's what we're really trying to do here. These are the tools that we have available now or coming soon. I'd say so. The newest one is a lead report card that helps maximize lead points across 3 different metrics using energy model data directly. So more coming there. The next one should be number 2 there. So the next update is the CalBEM project. So we were actively until about this week getting to the point where we could share the tool. Hence the kind of static images here, but we are to that point. And so the project is a desktop app and then 3 dashboards that will be hosted on BEM Toolbox, but then the desktop app helps you select a Zebiak model file, and it will help upload results and inputs data files up to the cloud, where it will kind of parse that data and generate 3 dashboards. So there's one focus on results, energy results, and the different compliance metrics, space data focused on lighting and ventilation. And then HVAC, focused on heating, cooling, coils, and fans. And to give a little snapshot of these, these 3 images are from each of those respective dashboards. And I submitted these slides a couple weeks ago, but today we're to a point where I can actually, share these dashboards. So, you all can test them out, or I can demo it on my computer for you later. So yeah, excited about getting feedback and testing on that one. So update number 3 is related to my power talk from last year, which was a vision for the future of BEM reporting and focus on automation. And that was just before I was awarded an IBPSA project through the Building Data Exchange Committee on developing a vision, engaging with key stakeholders, and then developing a roadmap on automated reporting for compliance incentive certification. So something, yeah, we've been doing a lot of work on through that IBPSA committee with another project coming up. So we're just finished the last interview last week, actually. So now I'm working on kind of wrapping that up and then getting the roadmap out, and that should be out by the end of the year. The last one, hot off the press, this was shown at Greenbuild a couple of weeks ago. So U.S. Green Building Council had reached out earlier this year after seeing the Power Talk from last year, actually. And we were talking for several months, and I'm working on helping them develop, and this is an early version of the work in progress, but it's a streamlined energy simulation documentation tool that will work for version 5, LEAD v5, which is, they just launched at Greenbuild or just invited project teams to submit early. So excited about the streamlining potential here, and the idea is we will develop automated ways of getting data out of energy modeling tools into a JSON file. And currently you can kind of drag and drop that data file. It will pre-populate this web app, and then the user can kind of review or fill in other data to get the inputs, energy results, calculate performance score for LEAD. And yeah, that's it. And I guess if you're interested, come talk to me, or you can talk to Elise on the CalBEM project and those dashboards if you're interested in testing those out. Thanks. Didn't even need those.
Hey. Everyone's being so responsible with the clicker and leaving it here. Awesome. Up next is Michael Sawford, and on deck is Matt Zebiak.
Thank you, Elise. Okay, hello everyone. I'll keep up to time. Welcome to this CalBEM Power Talk. I'm Michael Sawford. I'm with A2 Efficiency and co-chair of Working Group 3. I'm here to share a little bit about the IBPSA-USA Strategic Education Plan, which was a plan to build a roadmap for developing accessible, impactful educational content for the building energy modeling community. Think about practitioners. A central question that drove the project was, how do we train the next generation of BEM experts, as in, again, out of school, in the field, learning what to do. There's already fantastic educational content out there from ASHRAE, AIA, Quebec, Energy Codace, and others, vendors, etc. But most modelers still learn on the job. That means that there are still gaps in fundamentals, in applied practice, and in ongoing learning in general. IBPSA-USA's Education Committee asked A2 Efficiency to create a plan that could fill those gaps and be practical and scalable and sustainable for a volunteer-driven nonprofit, which is obviously resource-constrained in some ways, with open-ended problems like what tools can be used, built to share educational content effectively, both from a course creation standpoint, authoring, etc., and cost. What educational content is needed, who the audience actually is for this material, and to try and find a solution that includes a self-sustaining business model, so no big ask, if possible. Before designing the solutions, we first had to understand who we're actually building this for, how big the opportunity is, like what resources need to go into it, and what are comparable organizations doing. Our research looked at memberships across major industry organizations you'd be familiar with, AIA, ASHRAE, USGBC, some regional and statewide groups as well, and particularly looking at how their educational ecosystems function, noting where some have formal credentials, which some actually have them professionally required, and most supporting some form of credential maintenance. From our research, we estimated, in alignment with what Kyle shared earlier today, there are between about 3,000 to 6,000 active modelers in the US, which is a substantial community of active professionals, but one that does need smart, scalable support, as if you divide that by the population of the country and that square footage you mentioned, it's not many people per state. Before I get into more details on the report, I wanted to zoom in on IBPSA-USA first. It's a community built around research and science. Members are software developers, consultants, and academics, and that's kind of what makes IBPSA-USA unique. It's powered by volunteers, researchers, and practitioners all together. The organization operates through volunteer board committees and local chapters, supported by a management team that kind of handles the day-to-day and infrastructure. If you're already a member, thank you. If you're thinking about joining, this plan shows how membership directly contributes to growing the profession. For those members here today, or prospective members on the fence, or people maybe seeking value of membership in IBPSA-USA, what would you as an IBPSA-USA member want IBPSA-USA to provide for educational content? If you think about it, what would you want the organization to deliver? More courses, certification pathways, a knowledge network connecting external resources in one place? Something to think about when you have 2 minutes, as Josh reminded me, so we'll get into the next slide. Either way, as Margaret Mead said, and I've adapted her words here slightly, never doubt that a small group of thoughtful, committed IBPSA-USA members can change the world. Indeed, it is the only thing that ever has. This brings us to the report. I've had 3 core goals. First, defining IBPSA-USA's role in professional education for modelers. Second, identifying knowledge gaps from entry-level fundamentals to best practice workflows to advanced topics like new simulation methodologies and technologies. And third, all aligning this with IBPSA-USA's scale, audience, and mission. With a clear idea of the landscape, initial ideas for content needs, the next steps we're trying to identify a method to deliver it and a framework for organizing it. For the framework, we presented an organizational framework for IBPSA-USA's content to organize existing content and to set up ways to think about new content creation and how that might fit into the LMS to deliver it. And for the LMS, we reviewed several learning management systems, both on the shelf and off the shelf, and open source frameworks designed for maximum customization. Some key considerations were format and access controls for hosting courses, course authoring, user-tracked progress, managing certifications, available integrations with payment systems, etc., and many other things. We scored several LMS options on functionality, scalability, and cost, recommending a system that fits IBPSA-USA's volunteer model while still providing the features that they would need. And lastly, to shape the roadmap, we developed a series of project ideas that were developed and prioritized by the Education Committee of IBPSA-USA, with those ones prioritized developed further, and the rest kind of left as breadcrumbs. So the roadmap outlines the journey, year 0 to 3 years, launch a new LMS, publish a refreshed BEM fundamentals course from an existing in-person course that they would have developed. Years 3 to 5, develop mid-level training, such as best practice applying ASHRAE PRM, for example. Years 5 to 10, establish a formal BEM credential with ongoing training and credential maintenance to try and build on the business model. This roadmap isn't the finish line, it's just the starting point. I hope that members and educators and industry partners will pick up these project ideas and adapt to them and run with them. You can find this report soon, perhaps on the IBPSA-USA site, if it's not already available soon. If this inspires you to pick up one of the ideas in the report, make it your own, take a look and share your thoughts and get involved. Thank you.
Awesome. Thanks, Michael. I'd like to welcome Matt Zebiak up next, and John McHugh is on deck.
Hi, everybody. Good afternoon. My name is Matt Zebiak, and I'm here to talk about what we're calling a front door to MIDAS. This is a new tool to explore both utility rates and marginal GHG signals in California. Now, for those who are not familiar, MIDAS stands for the Market Informed Demand Automation Server. This is a database operated by the CEC that houses all of the time-varying electric rates in California. There are a lot of them, as well as the marginal GHG signals in 11 distinct regions throughout the state associated with the grid, as well as the dates and times associated with California's flex alerts, which are times when people are asked to curtail their energy in response to severe events or grid emergencies. So basically, MIDAS has tons of valuable data inside of it. But what is it like to use? In order to use MIDAS today, you need to be familiar with how to pull code from GitHub repositories. You need to know how to extract information from complex data structures. You need to know what an API is and how to use it. To those of us without a CS degree, this can feel a little bit like hacking a mainframe. And this is kind of a shame because we in this room as building energy modelers are doing such great work to understand how changes that we make in the built environment translate to energy savings. But as was mentioned in today's keynote and mentioned in a lot of talks today, it's really helpful when we're talking to the broader community to not just talk about kilowatt hours and therms. Not everyone knows what that is. It's helpful to take that next step and say, what does this change mean in terms of how much a customer is paying in their utility bills? What does this mean in terms of greenhouse gas emissions reductions? And what does that mean for our progress towards our climate action plan? So MIDAS, in theory, has all the data that lets us take our analysis to that next level. But unfortunately for a lot of us, it's just kind of tough to use. So in classic infomercial time, this led us to say there has to be a better way. And that led us to create this incredibly simple interface. You can see graphic design is not my passion. This is a very, very bare bones, but very functional interface that is living now in a web app that uses simple filters and buttons that allows you to interactively explore all of the data that exists in MIDAS. So it's worth saying there are over 50,000 different utility rates, both present and historic, and they're organized by rate IDs, which are not really decodable. So this helps you to match rate names in plain English to rate IDs and to explore the rates that are available in different regions or in different sectors. We designed it to be easy to use, so if you're just logging on for the first time and need to pull data on 1 or 2 rates, you can do that. But we also designed it around power users who might be running thousands of models and trying to do thousands of bill impact analysis or statewide GHG accounting. So it's very suited to automated workflows as well. And what this means is that our community can have access to the most up-to-date utility rates and even utility rate forecasts a little bit into the future. And this allows us to take our energy consumption estimates and translate them into precise, accurate bill impacts for our customers. It allows us to also compare what happens if we take the same building and we move it somewhere else in California. How does that change based on the rates that are available in a different part of the state? It can make our analysis, in other words, more specific to our geography and our energy provider. So I'd like to extend a thank you to Southern California Edison, who's been supporting the development of this web app. As you can see, it's still pretty early phase, but if you'd like to use this, it is live now at midasinterface.com. So please feel free to check that out. And I'm here if you guys have any feedback. Here's my contact information. I hope this will be a useful tool for all of us, and we look forward to developing it further in the future. Thank you.
All right, you know him, you love him, John McHugh.
Oops. Oh, not red button. What is this? Oh, I see. There we go. Good afternoon. I'm John McHugh, and I'm going to talk about what I think is a foundational concept for using the performance approach. And the title has to do with a life cycle equivalency method for using the performance trade-off method. As you all are familiar, we have a series of prescriptive measures that are defined in terms of cost effectiveness using a life cycle evaluation of each of these measures. And they're, as the Warren-Elquist Act asks for, they need to be cost effective on a life cycle basis. Those measures end up being the basis of the performance approach. But in the performance approach, we do the trade-offs not on a life cycle basis currently, but on an annual basis. So for that flexibility, you can trade off your envelope against more efficient equipment. And the main thing to note out of this slide is that envelope lifespans are somewhere on the order of 30 to 50 years, whereas the other equipment, the non-envelope equipment, lifespans are typically 15 to 20 years. And one of the ways that some standards have tried to address this is looking at a maximum building envelope load. And some of the methods that might be used are an overall UA. And you know that, for instance, the state of Washington says the overall UA can't be 20% greater than what the prescriptive requirements are. Another way of doing this is in terms of doing a simulation of the envelope and then maintaining the default efficiencies of the other components, and that's what ASHRAE 90.1 does. And what I'm going to talk about is something a little bit different, which is to actually look at evaluating the life cycle energy of the proposed design to what it's supposed to be equivalent to, which is being equivalent to the prescriptive requirement. And so what this does is it makes a prediction that the non-envelope measures after your first 15 years that your air conditioning has failed, your lighting is being replaced, that's going to be replaced with equipment that is meeting the prescriptive efficiency requirements, not that it's better than prescriptive to offset the reductions in the envelope efficiency. So using this equation here, I have this example of this is the residential standard, and we have what is known as high performance walls and attics. A high performance wall has R5 continuous insulation, and the high performance attic has R19 insulation below deck. And the current trade-off would allow you with a high efficiency air conditioning and water heater to essentially remove that continuous insulation from the wall and reduce the insulation underneath the roof deck to R4. With this approach of using a life cycle evaluation, you essentially end up with a 2-to-1 ratio in terms of the life of the envelope versus the equipment. And you can either get rid of the continuous insulation in the wall or get rid of the additional insulation under the roof, but not both. And this gives a sort of long-term example of what the impacts are. So this first dotted line, the y-axis is the energy consumption relative to the prescriptive baseline. And during that first 15 years, it's matching the consumption of that prescriptive baseline. Whereas after year 15, you're using substantially more. And this shows the life cycle or the cumulative energy consumption. You can see after 30 years that you're approximately using 10% more than the prescriptive baseline. And using sort of this 2-to-1 approach, what you end up with is now my envelope actually has to be more efficient than it would have been, and I can't trade off as much equipment efficient. Well, for the same amount of equipment efficiency, I have less envelope efficiency. So the first 15 years, I'm actually lower than the prescriptive requirements in terms of the energy consumption. But after year 15, again, I also have a higher consumption. And what this shows is that at the end of 30 years, on a life cycle basis, I'm at parity. And so there's a 9% savings. And so does that 9% save, what does that mean? And just as, as a point of comparison, somewhere around a 4 to 5% per code cycle. All the measures that we have in a code cycle are around 4 to 5%. So with that, I thank you for your attention.
Thank you, John. We're going to go into a break next, and then after that is the first working group breakout session.